Hello everyone and welcome to the Autodesk Advanced Manufacturing Summit. This session is about programming complex parts easily with PowerMill. I will show you some workflows on how to generate a toolpath from a CAD model, which will be a simple part workflow by importing the model, creating a block, some work planes, load cutting tools from the database, create roughing strategies, do some rest roughing, look into finishing strategies, perform some toolpath simulations, and write an NC code. The next half of the course will be a little bit more complex because we look for advanced workflows for complex parts. We will look at 2.5D features, multi-sided roughing using the stock model, what we can do with Toolpath Editing, have a look at 5-axis simultaneous milling using collision avoidance, how we can make utilization of special tools, and drilling some holes. After that, we will perform a machine simulation. I hope you will enjoy that. My name is Alexander Keil. I'm working as an implementation consultant at Autodesk's Global Consulting Delivery. This session will be mainly live in the software, so I will switch over to PowerMill, which we can see here. I want to start a new part. So how do we get the new part in? That's easy, like dragging and dropping a file into the PowerMill window. And we have imported the part. For importing, you can not only use any Autodesk formats, but also use industry standard formats like IGES, STEP, VDA, or you can use proprietary formats from most any CAD systems that are relevant on the market, like using cut part files, 3DM, or Unigraphics or Siemens NX files. So after we have loaded our part, we have to create a block of material which we want to cut the part out. So I go for the block of material and select to calculate the material for me. I will go a little bit deeper in that to have some material to clamp my part on and accept it. So material created. This block can not only be defined by the size of the part, but you can also import a 3D model for being the block, for example. The next thing will be that we need a work plane that we want to use for creating the toolpath from. So I go and create a work plane for me. The work plane has multiple functionality. One thing, it defines the 0 point of our toolpath and of the NC program that we create later. In this case, I will call it G54. But it will also give us the direction from where the tool will access the material. And regarding the tool, I need some tools to cut this part. So I go for the tool database, open it up, and select tools that I want to use. So let's see what tools do we have. For the roughing, I want to go for a 20mm tool that we have here. It has a tip radius of 3mm, so I create this one. The next thing I want to have is a finishing tool. And for the finishing tool, I will go for a 10mm tip radius tool. So let's see what we have there. I will go for the 10mm with a 1mm tip radius. I tell it also to create this one. And I know that we will have to finish off some of the big surfaces on the part. For this one, I will go for a ball nose tool with 12mm diameter. So I want to create this. And I will know that in the edges, we have then some rest material that I want to finish off. And I go for a 5mm tool. This is a little bit too short, takes a little longer one, and create this one for me. We can also define tools inside of PowerMill. If you go here for creating, for example, a ball nose tool, and we make it a 3mm ball nose, call it ball nose 3. Then we can go for a shank that it has. Normally a ball nose of 3mm most commonly has a 6mm shank and something like a 10mm cone to go to the 6 millimeters. And it will sit in a holder. So we go and create a holder. In this case, I want to select the holder again from the database. Let's see what we have here. I go for this holder, apply. And the last thing I have to tell the tool is how long it should stick out of the holder. For this case, for example, 50 millimeters is a little bit too long. Let's say 40 millimeters. It should stick out of the holder. And I close this one. All parts that get created in PowerMill can be found on the left side in the PowerMill Explorer, which you can see here. And you see the tools that we have created, some from the database, some directly in PowerMill. And I want to start my toolpath using the 25 millimeter tool. So I double click it to activate it. And you can see it becomes active also in the graphics. To work on this part, I first want to rough off the excess material. For that, I go for an area clearance toolpath. There are a variety of strategies that we can use to clear off the material. In this case, I will want to go for a model offset strategy, which uses the contour of the model and offset it to the outside. So the milling will go from the outside of the material to the inside to get nice, clean cuts. The step over for the tool should be a little bit bigger because we have a 20 millimeter ball nose. We can easily go for a 10 millimeter step over, and the step down, I just keep it like it is. And I calculate the tool path. So happy with this one. I will close the form, and we can see that we got a very nice tool path all the way around, except on the inside of the part, in the small hole that we have here, there's no tool path. And the reason for that is that our tool is too big to fit into this area. But I want to go roughing with a big tool because it can remove more material in shorter time. So what I need now is a rest roughing to cut the details of the part and clear off the excess material in the hole that we have here. I just created here the rest rough, giving the name rest rough. And I now want to select the tool. I could either do that in the Explorer like explained before, or I simply go to my toolpath form, go for the tool, and select the tool that I want to use, which is a 10 millimeter tip radius tool. Now for rest roughing, I want to have a little bit smaller step over because a 10 millimeter tool will not work good with a 10 millimeter step over. So I'll go for a 4 millimeter step over and for a 2 millimeter step down for this tool path. Now, how can it know where rest material on the part is? To define that, I go to the rest material page, select I want to have the rest material calculated from a toolpath. I open it, take this one, and I can see I did not name it. So sorry for that. I will give it a name now. So it's a rough toolpath that we have used before. Simple as that. I can now press calculate. PowerMill will automatically detect where the last toolpath had left over some material and only create the toolpath where really needed. So you can see we have here some toolpaths that will cut down the steps that the last toolpath has created. And you can see that it nicely went inside of the hole and roughed the material out there. The next thing is that I want to go to finish some surfaces. And first of all, I want to go for the flat surface that we have on the outside here. And I will stick with the 10 millimeter tool to do that because it can do a big step over on the flat areas and cut a lot of material. So I go for toolpath strategies, go for finishing, and here we have the variety of different finishing strategies that are available for us. On this example, I keep it simple and just go for the offset flat finishing, accept this one. I will go for a finer tolerance, like 1/100th of a millimeter, and a little bit bigger step over for this tool. I want to have 6 millimeter step over. And that's all that I need to define for this toolpath, because it will find the flat areas on the part by itself and create a nice toolpath for us, like you can see it here. I give it a name so that I can recognize it later. So now we are left over with some freeform surfaces on this part that we have here, 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 and in the inside. I want to use a different toolpath to use it. But what should I take? We have different strategies that are perfect for flat areas, and we have different toolpaths that are good for steep areas like this one. In this case, I will use a combination strategy for both areas, flat and shallow, and this is the steep and shallow finishing strategy. But I want to define it where it has to mill. But before I can do that, I select the tool that I want to use. In this case, I want to use the 12mm ball nose tool to cut the part. And the area that I want to cut will be defined by a boundary. So I already selected the surfaces I want to use. So I will go for a selected surface boundary that gets easily calculated. And then we let the toolpath calculate inside of that boundary. Oh, I can see I made a mistake. I didn't set correct step overs. Nothing easier like that. I go for recycling the toolpath for my settings and change them as intended. So I want to have a step over of 0.5 millimeters for the steep and for the shallow areas. And the shallow areas I want to have cut in a spiral move. I want them smooth and have a center line cut. Recalculate. And now the toolpath that gets generated looks much better. And I will keep that one to go on with it. But I can imagine that we have a lot of material left in the edges of this part. And that's the reason I want to use another finishing strategy. So I will go for a corner finishing to cut the material in these edges. Here I will go for the 5mm ball nose tool, and I will deselect the limits I've set before. Want to go for a little bit finer step over by defining the cusp height to be not more than 1/100th of a millimeter. But how should it detect the corners it should go? So I just go and select the tool that I used before, which was the 12mm ball nose tool. Give it a name, press calculate, and here it goes. We get a nice toolpath to cut the rest material in the edges that we have. So now it would be good to know if the toolpath that we created really will cut the part like intended. And we have a solution for that. I will go for the roughing again and activate the simulation. So we get the simulation toolbar in the top. I will switch on that it also simulates the material for us. And I will drag the speed a little bit down so that we can see how the material gets cut. I press play, and now you can see how our tool goes along the toolpath and cuts the material. Let's pause for a moment. So we can see here all the toolpaths that we got and how it cuts the material. And we can get a little bit faster. So I drag up the speed of the simulation and play it. And even while playing the simulation, I can rotate the part and have a look on different areas and if the part cutting goes like intended. Directly after the roughing toolpath, we will go for the rest roughing and simulate this one. So I activate it, tell it to simulate, and play it, and you will recognize that the rest roughing toolpath will create a different color. That's by intent, so I can see where this toolpath had cut the material and where the roughing toolpath had cut the material. That gives me a good idea on how much material this tool has to cut. Next, we have a look on the finishing, and we will simulate this one. Okay. And we can see that it has nicely removed the material on the flat areas of the part. Now let's see what the steep and shallow finishing does for us. Again, we start the simulation and have a look. In a moment, we will see how we create an NC program. You could also have created the NC program first and then run the complete simulation in one go through, so you can see the complete NC program cut on the part and not simulating each individual toolpath. But I thought it's better to explain it like this. Okay, let's go for the corner finishing, which is our last toolpath on this part, and run this through. You can see it's first cutting the steep areas and then cutting the rest areas where the 12mm ball nose tool has left over some material. So now it looks very nice, but how it looks in metal, I can switch to a shiny view and see, yes, this is the part that I want to have. So I will leave the simulation and create an NC program from this toolpath. To do so, I go for creating an NC program, and I will select it to be named Coaling. I want to select a post processor that I want to use, and I will now add all toolpaths that we have created and add them to the NC program. You can see them all listed in here. Now I select here the output work plane, which will be our G54 that we created before. So this will be the 0 point that you have to measure on the machine to run the program. And we can write the program to the machine now. It just takes a few seconds for the NC program to create, and we can now have a look on it and see the G code that you can run on the machine. So happy with that, we can go for the next a little bit more complex part and see what we can do for you there. To go for the next part, I will now save our PowerMill session. This is our coaling project. It's always a good idea to save the sessions, because then I can access them later on and do changes, or I can use them as a template for new sessions with similar parts. Let's close this one and go for the next part that we want to have a look on. So you can see this part is a little bit more complex and more of a kind of a real world part that you would have to cut in your workshop. But the way we do it, it's mostly the same that we did on the simple part. So let's see. I have here already a block created, and we have created some toolpaths as templates. This is how most professional people work. They create themselves templates for similar situations. So here there's a roughing toolpath template, and you will see that it is the normal toolpath template that we have seen before. Call it rough again, but all of the fields are pre-filled with sensible parameters that we want to use again. You can create your own templates by simply creating a toolpath and saving the settings as a template. So I will calculate this one, not talking too much to it because we have created a roughing toolpath before. The thing I want to change now, I want to create rest roughing, but not based on the toolpath, but based on a stock model. A stock model is like the state of the toolpath at that moment in time. And to create this one, I go to the stock model page and select that I want to put the toolpath into the stock model and calculate it. This gives us the ability to see how our material looks like after this toolpath has run. So quite happy with what the tool has done. Going for the next toolpath, and this one will be the rest roughing. For the rest roughing, the only change I do according to what we did last time is I go for the rest, and this time I don't select to have the rest from the toolpath, but I want to use the rest from the stock model. I select the stock model to use and the last toolpath that has run before I want to calculate this toolpath. And I let it calculate. Now PowerMill will accurately calculate for us the difference between the stock model and the part that we have loaded, and only generate toolpaths exactly where it has to cut material. So we don't waste time and cut air moves. So I'm happy with this one, so I close it. But wait, I'm not totally happy, because I want to use this toolpath for the freeform surfaces, but I don't want to use it for the simple 2.5D pocket that we have here and here and here. But what can I do? I don't want to create another boundary and see if it's right. I like the toolpath what it is like at the moment, so I go for Toolpath Editing. Toolpath Editing is a very powerful functionality in PowerMill. So one type is, for example, limiting toolpaths. I can go on a certain position, like this one, accept, and ask it to only keep one side of the toolpath. It will always keep the side where the arrows point. So I will accept this one, and you can see it is got exactly there, and this pocket is not milled anymore. So I go now for the Y direction, doing the same. I want to have it cut. Let's zoom in. I want to have it cut here. Keep the backward part, okay. And I'll go for the opposite side and keep the other side. Now we have the rest roughing toolpath like intended. And during the toolpath edits I did, it automatically calculated all leads and links for me to be collision free, so that I don't get in trouble with the cut toolpath. Now I go for my rest material, which is in my stock model. I will add the toolpath to it and calculate the rest material. And you can see it only removed material from the stock model where we have also our toolpath, and the pockets are still intact. These are the areas that I want to cut next. So I will hide my stock model for the moment, and I want to use 2.5D strategies to cut that easy parts on my model. So I go for feature recognition. It will analyze my part, and let's see what it finds for me. Yes, for example, here we have an open side that I would like to use, and another one over there. And even here we have a pocket that I want to use. I will accept them all. Now I want to use a toolpath that is more like a 2.5D toolpath to cut off this edge. So I go for the next toolpath, and let's first cut the pocket that we have up here. In this, I have to select the feature I want to cut, which is my pocket that is on the top. And I also go for rest machining here, because I only want to machine where material is left. So I select my rest material model and select the state of rest roughing. I will calculate it. And you can see even though it is a different strategy, because it's a 2.5D strategy, which is milling the feature, it exactly knows where material is and where not, and creates only the toolpaths where needed. The next thing, I want to cut the pocket on the side that we have here. I again select a strategy to do so. Wait a moment, the form will open up. It is the right side that I want to do first. I will go and select the feature that I want to cut. This is this one. But wait, if the tool comes from the top, I cannot really cut this feature. So to make a multi-axis toolpath, I have to create a new work plane. And nothing easier like that. I just select a flat surface in the area that I want to cut. And you can see with the new work plane, it creates a tool direction that is according to that. Let's calculate the toolpath and see what it's doing. Oh, I forgot to give it a reference for the rest material. That's right. So let's go for the rest material, select also the stock model there, and do the calculation. Now our toolpath should be calculated fine. And we can see here the result, which is a very nice rest roughing for the pocket that we have on this side. I have the similar situation on the other side. So the easiest way is not to load another toolpath strategy, but make a copy of the one that I had. And I will name this one not side right, but side left. I will then select the different feature, which is the, oh, that's the wrong one. Let's see. Here it is. It's a good thing that everything that I select will be graphically displayed. So this is a side that I want to cut. I go for a work plane, create a new work plane that is perpendicular to the surface that I select, and I can calculate the next toolpath on the other side. Okay, and I will accept this one. Now I can add both toolpaths to our stock model. So I go for the first one, and I will add it to our stock model, and I will select the next one, also select it to the stock model. And nearly I forgot the pocket on the top. This one will also be added to the stock model, and I will calculate it. Make sure that I've selected the last state of this stock model to be calculated. And we can see how nice it cut off this 2.5D geometry, not using a 3D toolpath, but getting a nice clean toolpath for this 2.5D features. So I hide the stock model for the moment because I want to go for finishing and show you some features there. We have a steep wall here that I want to finish. And I want to do it with a short tool because I want to have a good surface quality. So I go for a strategy to do so. I will select my toolpath strategy I want to use. And calculate the toolpath for that. Okay, so toolpath is finished, but when I go for simulating this one, I give it a name. It is our wall. You can see that it's extremely close or even hitting the walls on this side. And also, if we go to the top, we get very close to the walls there. And even I select the lower part of the toolpath and simulate there. You can see it's extremely close to the walls, and I really don't want to cut it like that. So what can we do? One thing is we can use Toolpath Editing again, because Toolpath Editing would also be capable of changing the tool direction. we have a dynamic tool control for that. So I could use this one to drag the tool in the direction which I want to use to cut. And I could then accept this toolpath. Yeah, let's do that for the moment. So you can see we have now a different direction. And if I now simulate this toolpath again, oh, sorry, I should have accepted the change. Let's do it again. Get the tool to the front here. Go for the dynamic machine control, and then simply drag the tool to come from the other side. We will update the toolpath on that, accept it. And if I now simulate it again, you can see that we are clear of the wall on top here, but I'm a little bit concerned about the edge that we have here. So I would prefer to have PowerMill calculating the optimal position of the tool to cut this toolpath. Said that, I go for the settings of this toolpath and tell it I want to change them. And I want to have it calculating an automatic tool axis. So I go for collision avoidance, which means it should be clear of any collisions. And in the collision avoidance, I give it a holder clearance of being 1 millimeter and a shrink clearance of being 1/10 of a millimeter. But we want to have a smooth toolpath with a smoothing distance of 40 millimeters, and it should automatically calculate the optimum angle of the tool. Let's see what this one does. Okay, it refuses because I did something wrong. I delete it and get a toolpath for the wall again. The reason why it refused to calculate the toolpath was because I've used the dynamic machine before, and that doesn't fit together. So again, I go for automatic collision avoidance with the original toolpath that we had before. I want to have it automatically calculated. And let's see what it does for us now. You can see when I do it correctly, it nicely calculates the toolpath for us. And we can clearly see that the new wall toolpath, if I simulate it, creates a toolpath where the tool nicely leans away from the collision areas and gives us a toolpath that can run on the machine securely and safely without making any head about collisions, because it automatically avoids them, and we are happy with this one. The next toolpath I want to use is for the surface I have here, and I want to have a very nice surface finish there. So I will go for the next toolpath, and I want to get the nice surface finish. I want to use a special tool. If you look on this tool, you can see it's not only a tip radius, but it has also multiple radiuses on the cutting area on the bottom of the tool. These tools are meant to give high performance cutting and a very good surface finishing with a very little cusp height. So I select the surface here, make sure that my tool axis is set to lead and lean, and will calculate it as special tool 5 axis. And just for comparison, I will create another toolpath. So let me have a look. I think this one has a diameter of 6 millimeters, so I will make a copy and use another tool, which will be a bowl nose 6 millimeter, which should give us the same toolpath. So here's a ball nose with a 6 mm. For the tool axis, in this case, I go for vertical, and I will calculate the same. And we will now have a look on the toolpath. To see what the difference is, I will go for a view and make a clipping of the view so that we can see the inside of the part. So I go here for the half of the part and put my tool here. In this instance, you can clearly see that my ball nose tool has only a single point of contact with the surface, and the spot that is milling is very small. And if we go up to this area, we can see we are even cutting in the middle of the tool, where the actual cutting speed of the tool is 0. So it's not very good. Let's see what we have done with the special tool. So I activate the toolpath with a special tool. And the first thing that we will recognize is that the tool is always going from the direction with the surface. This is because it has a nose which is perpendicular to the surface and has a 5-degree lead angle. What does that mean? I will show it in a minute. We go for dynamic sectioning again and have a view through the part in the middle. And then I will put the tool again on the area we had it before. And now you can see that the area of the tool that is touching here has a much bigger radius than the part that was touching with the ball nose tool. And also, if we simulate the toolpath, we can see that the tool nicely goes with the part. So we attach it here again, and we can see that it has a little bit of a lead angle, so that it always has contact with the same area of the tool and not with the center where we don't have any cutting speed. You can use this technique for, like this one, high performance cutters, or you can use it for barrel tools, or even for conical tools, if you like. The next thing that's very obvious to me on this part is that we have some big holes that we want to drill. So for hole drilling, I go for the hole features and tell it I want to create some holes in this part. To create these holes, I just select the surfaces that I want to use. Let me have a quick look if my settings are right. Missed some setting. I will give it a name. These are my bushings, and I want to apply this one, and it finds the holes automatically in the part for me. So I can close it and have a closer look on what we are doing here. So let's hide some other things that I don't need anymore, which is the pocket, and also here the curves that are created. I don't need them anymore. And have a look on the holes that got created. You can see it created compound holes, which means the diameter upper here is bigger than the diameter more below. And it created some additional holes for us that I don't need, which are these ones, so I can delete these holes for the moment. To drill the holes, it's easy like finishing or roughing the part. I go to select another strategy. In this case, it is a drilling strategy. And I will go for a simple drill in this case. I will have to select the tool that I want to use. There should be a 38 mm drill. that I can use. The work plane should be the one that comes from the top. The tool axis will be pure vertical for this one. And then we can calculate the toolpath. I will simulate it from start, and you can see that it nicely goes into the holes. It has automatically selected all the holes that are from the same size and creates the drilling toolpath for us, which can also be written out as drilling cycles by the post-processor. If you're wondering, we got a red exclamation mark on this toolpath. The reason is that these holes are kept by surfaces that I don't mill inside while milling, but they are ignored while drilling, but I'm hitting them, so it gives me the hint that I drilled through some surfaces. But for drilling, this one is okay. The next toolpath I want to use there is I want to mill out the rest of the material in the holes, because I had a smaller diameter drill than the hole diameter is. So I want to go for a helical milling operation. I select this one. The tool I want to use for the helical milling is a 30 millimeter end mill. We can already see it here in the graphics. Going for the drilling, I want to go for a pitch, which is a step down per turn of 5 millimeters. And just select to calculate. And as we have a compound hole with multiple diameters, you can see it all automatically recognizes the change in diameter and will create the toolpath accordingly for drilling. If you have often to drill the same holes or holes of different style, and you know you want to have a certain order of drilling operations, you can also go and create some drilling methods. If we look into a drilling method, then you can see a drilling method can be created from ordering different drilling strategies behind each other. In this case, we have a single pack. For spot drilling, it will use a single pack cycle. Then we have a chip break cycle used for drilling the complete hole. And after that, we have a reaming. And you can also tell it which diameters it should use. So it can be used for bushings like we have here. It can be used, for example, for threaded holes where you have to pre-drill and then tap the thread. Or you can even use it for more complex hydraulic port milling. In this case, for these easy holes, I don't need it at the moment, so I delete the toolpath. So we are quite to the end of this part 2, but how can we make sure that this one will work on our machine? Especially the 5-axis simultaneous milling. I'm a little bit afraid that it might not work. So let's see what happens if we put the part on the machine. For that, we can simulate also a machine tool. So I activated the machine tool here. We can activate a toolpath and simulate the complete toolpath together with the complete machine. So it's a little bit boring for having a look on the roughing, because I know 3-axis toolpaths are often good and it will perfectly match the machine. But what is with the 5-axis toolpath that we created for the wall? So I will activate this one and tell it to simulate this. You can already see that it has turned the axis. And if we run the simulation now, you can see that it only turns the axis when it's needed to and when we have the risk of colliding anywhere. The rest of the toolpath where it has no risk of colliding, will be a 3-axis toolpath. So it has perfectly avoided the collisions with as less machine movement as possible. If we want to know more about how the machine moves, we can have an analysis of the machine movement. So I go for the machine analysis, wind back the toolpath, and run the simulation again. So now the simulation got recorded. I will save it. And then we can have a look on the movement that the tool does. So here you can analyze each axis of the toolpath that we have. For example, for the rotary axis of this machine, we have the movement here. And you can see the movement, how it goes. This gives you the ability to judge if your machine is moving soft and nice, especially when we move in a little bit closer. You can see that we have here mostly a good movement of the machine. I'm happy with that, and the machine analysis will make you sure that you get the best quality of part in the shortest time from your machine without stressing the machine too much. Now, I'm at the end of the short walkthrough through PowerMill with the overview we have seen. So what we have looked at is that is only a small overview of the functionality of PowerMill. If you want to see more, contact us or contact your local reseller, and they can help you and give you more information. What we have seen was an easy workflow on a simple part where we got the CAD into the CAM, we assigned some stock material, set the part 0 that we can measure it on the machine. We selected some cutting tools, cleared off the excess material, got a surface finishing, checked the results in the simulation, and wrote the NC code. For the second part, which was a little bit more complex, we did the same workflow, but with a bit other tools. So we used roughing from multiple sides together with the rest model or with the stock model to avoid air cutting. We edited toolpaths without recalculating to save time. And we were milling difficult areas very easy using collision avoidance. Collision avoidance is a 5-axis strategy, which we also use to utilize special tools and take the advantage of them. After that, we made some quick holes and drilled them into the part. And to be sure that this will run on the machine, we made a machine simulation. You will also be able to download a handout of this session, and you will have a description and a little bit more information on what I've showed you there. So thank you very much, and welcome to other sessions of our Autodesk Advanced Manufacturing Summit.